So let's start. I will introduce myself first. So myself, Anjali Negi. I am a PhD student in IIT Kanpur, in Department of Chemistry. So I'm pursuing my PhD in theoretical and computational chemistry. So for today live session, I will be solving 3 or 4 set of questions. So I will share my screen now.
Hello everyone. In this video, I will be solving GAY 2016 chemistry question number 3. It states that among the following, the most stable isotope to radioactive decay is. So we are given with 4 different options of lead where the atomic mass is varying. So we need to find out the most stable isotope among them. So before I go through the question, let's go through some basic. Here, the theory of radioactivity, it states that the nucleus whose N upon P ratio lies outside the belt are unstable and therefore they undergo spontaneous radioactive disintegration. The nuclei with N upon P ratio lying above or below the belt are unstable, so they undergo radioactive disintegration, giving out alpha or beta particle in such a manner as they will yield some stability or stable nuclei. So we can consider case number 1 where the N upon P ratio, so the N upon P ratio lie above the region of stability. This means that the nucleus contains too many neutrons. If it is above the if it is above the stability region, okay, so it will emit a beta particle or we can say an electron, in the way that a neutron changes into a proton and the n upon p ratio get lowered and come closer to the region of the stability. Okay, so this is the plot where number of neutron is denoted as capital N, number of proton as capital P, and the belt here is the belt containing stable nuclei, and the elements that is above or below are show radioactivity here. Okay. For example, this is the disintegration of isotope of carbon. Number 1, where the n upon p ratio region. Okay, so it that a neutron number of radioactivity here. Okay, 14C6 carbon is disintegrated as it and shows a beta emission, and it get converted into nitrogen with mass number 14, so 14 and 7. The n upon p ratio falls from 8 by 6 to 7 by 7, and it gets closer to the stability belt, where the ratio get convert from 1.33 to 1. And the case number 2 you can consider, where my n upon p ratio lie below the stability belt, and evidently the nucleus contains excess of proton here, so it will disintegrate in such a way that the new nucleus has a high value of n upon p, and therefore that it can come closer to the belt. This happens when by the emission of an alpha particle, that is a helium nucleus. So as a result, that the new nucleus has lower charge and lower mass. So the unstable okay. So the unstable nuclei continue to emit alpha or beta particle until a stable arrangement is reached. Now, the tip here is that the n upon p of n upon p is equal to 1 is for the element number up to 20, and the n upon p between 1 to 1.6 will be stated as the stable nuclei or nucleus. So we can say for that the n upon p ratio lying between 1.6 and greater than 1.6 and less than 1 are stated as unstable. So for the given question, we are given with the 4 different isotopes, and I have written here the ratio corresponding to them. So the n upon p ratio is for 206 lead 82 will be 124 upon 82, that will be 1.51. And similarly, if you calculate n upon p ratio for all of them, you will get to know that the most closer to n upon to 1. So what we need to check that the n upon p ratio of given isotope should be more closer to or in between 1 to 1.6. They are actually in between 1 to 1.6, but the more closer to 1 will be the most stable one. So here you can see that the more closer to 1 isotope is the first one. Okay. So among the following, the most stable isotope to radioactive decay will be option number A. And I will refer you to go through the book Principle of Physical Chemistry by Puri Sharma Pathania, edition 2001. And the NPTEL reference is the lecture number 24, Radioactivity Alpha Decay, by Professor H.C. Verma, Department of Physics, IIT Kanpur. I have attached the link. Thank you.
You have any doubt, Ashish?
Clear, ma'am.
Okay. Yeah, so I will move to other question. Question.
Hello everyone. In this video, I will be solving GATE 2016 Chemistry question number 48. This question states that a system is described by the following real wave function. The given wave function is like this. Here we have, okay, and it is divided into three regions: 1, 2, and 3. So we need to find the probability P of finding the particle in a region dx around the point 1, 2, and 3 in the given figure. So we need to find the trend of the probability, whether which one has the higher and the lowest probability of finding the particle in that particular region. So before getting into the solution, let's head into the basic of the question. So it comes from the postulate of quantum mechanics. So the first postulate of quantum mechanics is the state of a quantum mechanical system is completely specified by wave function psi x t. Okay, but we need to okay. Is completely defined by the wave function psi xt, but you need to note that the wave function psi doesn't contain does contain all the information about the system that we are interested in, but the wave function itself does not help and give us any physical interpretation. Okay, there is another idea which we can use, and that is what we call as Born interpretation. So this Born interpretation suggests that although the wave function itself does not have any physical meaning, but what will have the physical meaning is the psi star psi is multiplied. Okay, just write it down. That the psi star, that is a conjugate of wave function psi, when multiplied with wave function psi, when multiplied with psi x comma t, will give me the mode square of my wave function. Okay, and this is particularly the quantity which has a physical meaning, and it is equal to the probabilistic. So this physical meaning has a probabilistic interpretation. So this is what we call as Born. This will give me the Born probabilistic interpretation. This is known as. So this says that the wave function which contain all the information, although it itself does not have a physical meaning, but the psi star psi multiplied with psi, giving me the mode square of wave function psi. This will give me the answer to my question, that the probability of finding the system at a particular value of x and a particular value of time t. Okay. Correct. Okay. So now if I jump to solve my question, which was the plot where I was given a wave function psi. Okay, so this was 1, this was 2, and this was 3. Okay, this is my psi. And so again, remember that the probability that we were asked in the question itself, we need to, if I draw that plot, it will be mod of psi square. So because it is a psi square, so there will be no value in negative region. So my first plot will be like this. I'm just following the particular magnitude of each plot or value of wave function. So you will get probability value corresponding to each region. If I say this is P1, this is P2, and this is P3, then it will become as, so P2 has the highest value, then comes P3, and then comes P1. Okay. Now, the probability of finding the particle in the region 1, 2, and 3, in which follows the given trend in the figure, we had 2, 3. This is 2, then 3, and then 1. Okay. So the correct option is B. I will highly recommend you to go through the lecture Postulate of Quantum Mechanics 1 by Professor Sabyasachi Mishra, Department of Chemistry, IIT Kharagpur. I am attaching the link below. Thank you.
So if you have any doubt.
Clear, ma'am.
Okay.
Hello everyone. In this video, I will be solving GATE 2017 Chemistry question number 9. This question states that the electronic ground state term for the chromium ion in the given complex is. So we need to find the ground state term symbol for the chromium ion. Before that, we should go through some basic concept. We see that there are interaction. So there are 3 type of basic interaction, which are spin-spin coupling, orbit-orbit coupling, and the spin-orbit coupling. So the one coupling scheme that we go through is the LS coupling, which is the Russell-Sunder coupling of electrons. Okay, and another one is the JJ coupling. So basically, it is assumed that the spin-spin coupling is more than the orbit-orbit, and lastly the spin-orbit coupling. So and the first row transition series where the spin orbit, that is the J coupling, can be generally ignored. So for element with atomic number greater than 30, the spin orbit coupling become more significant, and the JJ coupling scheme is used there. But here we will see the LS coupling. So the quantum number determines how the electron interact the energy of the microstate depending on the quantum numbers ml and ms of the electron. So the ml magnetic quantum number of a single electron is equal to from minus L to plus L. And the capital ML is the total orbital angular momentum for total number of electrons, and it will be the summation of ML. And the maximum value of this capital ML is corresponding to the quantum number that we call as L. Okay, and so L is equal to the total orbital angular momentum quantum number. Okay, and we can generally define the microstate as due to this angular momentum is 2L plus 1. Okay. And the quantum number capital L alone does not define the term yet. So we need to consider the interaction of the spin of the electrons, and that is ms equal to spin quantum number of a single electron. And capital MS is the total spin angular momentum, that is a summation of each electron ms value. So the maximum ms value will give me the quantum number denoted as capital S. This is the total spin angular momentum quantum number, and the microstate due to this term is equal to 2s plus 1. Also, the spin quantum number ms of a single electron can be either plus half or can be either minus half. So when the spin of the electron interact, their spin quantum number add up and define the total spin angular momentum as capital MS. So the number of microstate due to the spin-spin interaction that belong to the term is 2s plus 1. Okay, and this is also known as the spin multiplicity. So this is also known as okay. Now considering D4 configuration, so we have orbital like this here, okay, and so the capital S, that is the total spin quantum number, will be for 4 electron 1, 2, 3, 4, that is the D4 configuration. It will be plus, they all are in the same spin, so either plus half, either minus half. So if I am taking plus half each, I will get capital S equal to 2. And for orbital quantum number capital L will be the summation of Li, that will be plus 2 plus 1 0 minus 1 equal to again 2. And the spin multiplicity, that is the 2s plus 1, is equal to here 5. And my L here is equal to 2. So this actually, I should tell you beforehand that the total orbital angular momentum quantum number, angular quantum number L, and the total orbital spin quantum number S, these two define the term symbol as here 2s plus 1, and so this is the spin multiplicity. And this is my capital L. If the value of L is like L equal to 0, then this will be denoted as S term. If it is 1, then it will be P. If it is 2, then it will be D. And so, if it is 3, then it will be the F term. And okay. So the construction of the term symbol is something which is the atomic term symbol contain 2 pieces of information. So they will tell me the orbital angular momentum of the atom, that is the L value, and they will also tell me the multiplicity, which is here spin multiplicity 2s plus 1, and these are denoted these are denoted by this simple method, that is multiplicity at the left hand side at the power of the term capital L. And here, please note that each term symbol, they represent a discrete energy level, okay? And so that we can place these level in a correct order by using some rules. So high multiplicity value, it will, okay, I just write it down, that the high multiplicity value will give me low energy. So if the multiplicity value is equal, then we go towards the value of L. So so here the high L value will give me again low energy. Again, if I have the same L and same multiplicity value, then there comes the term J. So the third term J, I will introduce it later. So here J, so J value is something like, if my orbital is less than half filled or more than half filled. So if it is less than half filled, then my J value will be low energy. And if it is my orbital is something which is more than half filled, then it will be, okay, wait, I made a mistake here. So if my orbital is less than half filled, then the low J value will be corresponding to the low energy. So low J correspond to low energy. And if my orbital, for example, here, if I am talking about D4 configuration, it is less than half filled, and for that, lower J value will be corresponding to the low energy term. And for more than half filled, for example, D6 or D7, D8, so those will be the high J value will give me low energy there. Okay. Now coming to the figure that I want to describe a little is on your right hand side. Okay, so I will just draw it. So yes, so if I so these are three different axes giving me the direction along either X, Y and Z. So if my capital L here if my capital here is this arrow correspond to capital L, which is orbital in blue color, and similarly for the same electron, if spin is denoted like this, which is S, capital S. So if you draw the cone around this, So when I'm talking about the coupling between these L and S, that is the orbital and spin, so I will get another vector which is capital J. So J is, so J is something like this. So J will be L plus S, correct? And this is the total angular momentum, J. And this figure illustrates us the LS coupling, okay? So J will be the cone corresponding to J, okay? Something like this. Now, coming to our question, which was asked about this complex where my chromium is +2 and the configuration I can write it as argon 3d4. So you can see that the electronic configuration for 3d4, I can write the S value So the S value will be 2 and the L term will again be 2 as I have shown earlier. So this will be corresponding to D term and the term symbol. For ground state they have asked, so definitely I can write the spin multiplicity as 2s plus 1 with my term L, which is here D. So this becomes, so if I include 2s plus 1 L, if I am including J here, so it will come as the suffix on the right hand side of the term. So J will be written here as here you can see. Again, as I have talked about, it is less than half filled, that is the D4 configuration, then the lower value of J will be equal corresponding to the ground state term of the particular term in lower energy. Okay, so that will be 0 here as J is corresponding to L plus S value to L minus S. So the L plus S value here is 4 and we have L minus S which is 0. So the lower value of J, that is 0, is corresponding to the ground state term. So you can write the term as 2s plus 1, that is 5d0. Here you can see that the correct option we are given with is the 5d option, where J is not written, but we can go with the 5d option. And the NPTEL reference that I will recommend you to go through is the spectroscopic term symbol. Sorry, there's a typo mistake. By Professor Debarata Mehti. So from Department of Chemistry, IIT Bombay. And here is the link below. Thank you.
So clear?
Clear, ma'am.
Okay. So we have time for the last question I am including. Okay.
Hello everyone. In this video, I will be solving GATE 2016 chemistry question number 52. This question states that the magnitude of the difference in the crystal field stabilization energies in delta naught, okay, and ignoring pairing energy, so of the given two complexes is. So to solve the given question, let's move into some basic, that is, the crystal field splitting in an octahedral complex. So it is denoted as when the 5 degenerate d orbital, when there is no interaction of the ligand. So it is in the ground state, and once it is surrounded by the incoming ligand, the degeneracy of the d orbital is still maintained, but it is above the energy level, ground state energy level. And then finally, as according to the approach of the ligand, here we are talking about the octahedral complex, so it will get split into T2G and EG orbital, okay. And the T2G orbital are such that it will be dxy, dyz and dzx, whereas EG orbital having higher energy will be dx square minus y square and dz square. So the dotted line here denotes the barycenter, and x and y value we can calculate them like this, okay. So yeah, I can write here. You can actually find out that the T2G electron, so each of them is stabilized by minus 4 dq, or we can write it as minus 0.4 delta naught. That is, delta naught is the unit of crystal field stabilization energy, and the EG electron is get destabilized by plus 6 or plus 0.6 delta naught with respect to unsplit barycenter, okay. So the total energy of the system is actually conserved before and after the splitting. Also, we need to note that the ligand which causes large splitting, that is the delta value is large for that particular ligand of the d orbital, are referred to as a strong field ligands, and the complexes such as this, having the strong field ligand, is known as the low spin complex. For example, ligand NO2 negative, this will for the D5 configuration, when the splitting is octahedral, so it will split into T2G and EG. But since my NO2 negative is the strong field ligand, it will make a large splitting of that is delta of the d orbital. So here the delta naught is very large. Here the delta naught value is larger than the pairing energy P. Okay, so what will happen, that the electron will get paired in T2G itself, and you can see that it will be denoted as a low spin complex. Now coming to the ligands which are weak field ligands, such as iodine, I negative and Br negative, this will cause a small splitting delta of the d orbital, and it will be referred to as a weak field ligand, and the complex will be known as the high spin complex will be formed, okay. So again, for the D5 configuration, I will be having delta naught value smaller than the pairing energy, so I can write it as delta naught value will be smaller than the pairing energy. So my electron, the 5 electron will get arranged as singly occupied. So EG orbital will also get occupied, and this is known as the high spin complex. So in general, you can go through the the crystal field splitting energy increases as the ligand varies in the following order. So this is what we called as, this is in increasing value of delta. This is from I negative to Cn negative. So Cn negative is the strongest strong field ligand, which will make delta naught splitting very high. And you can, in comparison to H2O, I am here making you note that H2O and CN negative order, because we have to solve the question which we have these two ligands in the same complex with the same oxidation state. Okay. So for the given question, so I am given with two different complex, Fe H2O6 2 plus and Fe CN6 4 negative. So in both the complex I have Fe2 plus. Again here I have Fe2 plus. So my electronic configuration become 3d6, and here also it is 3d6. You can note that H2O here will act as a weak field ligand, and here Cn negative will act as strong field ligand. So this will make a high spin octahedral complex, and this will make a low spin octahedral complex. Okay, and so I can just show that it will Eg T2G Eg T2G, and the filling will be, for high spin it will be 1 2 3 4 5 6. Okay, and for low spin it will be 1 2 3 4 5 6. Correct? Delta naught. So the CFSE of this complex will be, so it will be 2 into 0.6 and minus 4 into 0.4. Okay, so this will be minus 0.4 delta naught, and here the CFSE will be 6 into minus 0.4 delta naught, which will be equal to minus 2.4 delta naught. Okay, and so if I we are asked about the magnitude of the difference, okay, in the CFSE of each complex. So we just need to tell the magnitude, not the sign. So the delta CFSE for each complex will be, so if I am saying it as say it 1, this is 2, so 1 minus 2, this will be minus 0.4 plus 2.4, it will give me the value 2 delta naught. Okay, so the magnitude, whether it is, you can take it 2 minus 1 also, because we are going to get the magnitude only, so I will be getting 2. So here the magnitude of the difference in the CFSE energy in delta naught unit for each complex is 2. Okay, taking only the magnitude. So I will highly recommend you to go through the bonding and complexes 3 by Professor Debashish Ray, Department of Chemistry, IIT Kharagpur. Thank you.
So if you have any doubt, you can ask.
Ma'am, this one is clear. Ma'am, third question, उसका आंसर B नहीं होगा.
Third question, wait. बी मैंने ए बोला है ना, जिसमें लेड का मास है 206.
Not that one. Ninth question, 2017.
2017, okay.
Electronic ground
So
state
the lower
term
value
for
of J.
Yes. So you are saying इसका correct option है
3H. B answer. B. Option B.
okay, option B. I think chromium का electronic configuration D4, correct?
Yes, ma'am.
So then what is
Ma'am,
my mistake?
CN.
Yes.
CN is strong field ligand, ma'am. Low spin complex बनेगा.
Okay. Yes.
And all the 4 electron will enter T2G. There will be pairing of electron. We will have one pair of electron.
Okay. So I have to look into this one.
Okay.
Thank you. I have another question for two of you who are here. So yes, wait. When I'm saying multiplicity, correct? So multiplicity mein so if I have the net spin capital S value equal to 0, so it is termed as singlet, okay? And for the net spin equal to 1, it is termed as triplet. So any of you can comment on it, why we call it triplet and why we call S equal to 0 value as singlet?
Ma'am, net spin value will be 2s plus 1. If we put s is equal to 0, then we will have value 1. And if we put s is equal to 1, then we will have value 3.
Okay, yeah, that's another way of interpreting it. But the actual reason behind it is that there are the combination that we say, okay, whether it is a microstate or whether we say just mathematically the combination. So if you are calling it a singlet or a triplet, the reason behind is that there are 3 ways to combine a pair of electron to get the spin S equal to 1, but only one way to get the S equal to 0. So I will just, okay. You can see the tab, right?
Yes, ma'am.
Okay. So yeah. So for any 2 electron, so if I am having 2 electron, I can have the spin in altogether many combinations. So one is this, all 2 having up spin, all 2 having down spin. So one up, down, down and up, okay? And yes, so what happen is that the S value, the capital S value will be half plus half plus half, that will be capital 1, and here it will be again 1, here it will be 0, and here it will be 0, okay? And if you remember in the video I have shown the diagram where I have axes x, y, z, and then you have L, that is the orbital angular momentum, and S, which is the spin orbital angular momentum, correct? So it should be in xyz plane, rotating vector. So if I just denote simply, I am not denoting L or J here, but I am denoting the spin orbital angular momentum. So if I can draw for each of the electron, I will be having two different spin orbital angular momentum for these two electron, correct? So if they are having the spin value, ms value, that is plus half, so say both of them are having the spin orbital angular momentum vector like this, okay? So this is for s equal to 1. Now these vector can be arranged in different ways, like in the same, if I can have this is for ms minus half, so again, and then in this way. So there are in total 3 different arrangement, combination for the triplet, and for singlet for singlet it will be for s equal to 0. Only one possible combination will be here, that is why it is called singlet, okay? Another I will give you one problem of so if you have the electronic configuration like this, so it is 1s2, this is 2s1, and this is 2p1, okay? So this is the electronic configuration, and this is, you can say that this is the excited state electronic configuration corresponding to beryllium, okay? So if you need to find the term symbol for this particular microstate, what will be the term symbol? So I will just give you 1 minute to find the term symbol. So Ashish, you are solving it?
Yes, ma'am.
Okay. So I will just
Yes, ma'am.
keep it short. Find out the ground state term symbol, because there will be term symbol, I mean no, this will not be the ground state one, no? So you can find out all. So Ashish, I will start solving it, okay? You can match with me. So the to find the term symbol, we need to calculate capital S and capital L value. So for this configuration particularly, so there are two unfilled orbitals, 2s and 2p. So I need to consider both of them. So the 2 electron is in s and p orbitals. Okay, so my ml, I can say ml or L1 value will be for s orbital, it will be 0. Okay, and for p orbital, let's say L2, it will be, so p orbital, it start from +2, so it will be +1, so it will be 1. Okay, so the capital L value will be the summation of these L1 and L2. It will give me capital L is equal to 1. So this will correspond to the term P, capital P. And for the capital S value, this is interesting because it has combination. So I can either consider that both of the two electron are in up spin, so it will give me the value S1 plus S2 equal to 1. Okay, and if any one of them is in different spin, so it will give me the capital S value as S1 plus S2, that is plus half minus half, that is 0. Okay, so this will just give me the multiplicity, that is 2s plus 1 s. So it will vary from if my s equal to 1, so it will be 3, and if my s is equal to 0, it will be 1. Okay, so multiplicity can be 3 and 1. Now, so I have two different multiplicity, one term as p, so I can write it as 3p, I can write it as 1p, correct? And if I calculate the value j, so my j value is, what was the formula? L plus s. So this vector comes when there is a coupling between orbit and spin, correct? So when there is a spin orbit coupling, j comes, and this j, okay, sorry, wait, yeah, so it goes L minus S. So my J value will be L plus S, that is so L plus S, so 1 plus 1, that is 2. Okay, so 2, or either 1 plus 0, that will be 1, it will, okay, and 1 minus 1, that is 0, or 1 minus 0 is 1 again, so it will be 2 1 0. So I will have J value, 3J value, so 2 1 0 will be 3J value. Okay, so for 1p, actually for 1p where my S value is equal to 0, so when my S value is equal to 0, my J value will only be 1. And where my S value is for the multiplicity 3, that is my capital S value is 1, I will have J value as 2 1 0. Okay, so it will be 2, it will be 3p1, and it will be 3p0. Okay, now you can also arrange it with respect to the energy, I mean which term lies to which particular energy according to the rules that I have discussed in the video. Okay, so it's clear, Ashish?
Clear, ma'am.
Okay, so okay, that's all for today. Thank you.
Thank you, ma'am.